Deep inside galaxy NGC 5419, two invisible giants orbit each other, a pair of hidden black holes weighing more than 10 billion suns. Their gravity twists space-shaped stars and rewrites everything we thought we knew about the universe. Tonight, we're uncovering their story. If you enjoy this journey, please like, subscribe and share, and tell us in the comments, what would you ask a black hole if it could answer? Thank you for watching. Now let's begin. In the present epoch, the universe reveals itself on the largest scales as a network rather than a random scattering, and astronomers describe this pattern as the cosmic web, a structure in which matter is gathered into long filaments, dense knots, and wide, nearly empty regions called voids. Along each filament, gravity has drawn together dark matter, ordinary gas and galaxies over billions of years, so that the space between the big nodes is threaded by chains of galaxy systems rather than left truly empty. A galaxy group is a small collection of galaxies, often a few tens of systems bound together by a shared gravitational field, while a galaxy cluster is a larger gathering, with hundreds or even thousands of galaxies moving within a much deeper potential well, and these different systems sit at the crossing points and thicker parts of the filaments. When astronomers map the sky in the direction of the constellation Centaurus, they do not see the cosmic web directly, because the stars of the Milky Way form a bright foreground pattern, and the constellation itself is only a projection of nearer stars seen from Earth. But careful measurements of galaxy distances and motions reveal that this region of the sky contains a complex layering of groups, clusters, and filaments along the line of sight. Some of these systems are relatively nearby on cosmological scales, at distances of hundreds of millions of light-years, while others lie much farther away so that their light began its journey when the universe was younger, and this depth gives the Centaurus direction a rich three-dimensional structure that is not obvious from a simple optical image. Surveys that trace the distribution of galaxies through redshift, which is the stretching of light to longer wavelengths by the expansion of space, show that in this part of the sky, galaxies are not smoothly spread but instead collected into arcs, walls and nodes, and between these denser regions lie great voids where only a few isolated galaxies are found. The dark matter that anchors the cosmic web does not emit light, but its presence is inferred from the motions of galaxies and from the way it bends the path of more distant light through gravitational lensing and simulations that include dark matter and gas reproduce the observed pattern of filaments and clusters, remarkably well reinforcing the picture of a universe in which structure grows hierarchically over time. In the Centaurus region, as in many other directions, filaments feed matter into the sites of galaxy groups and clusters, with gas funneled along the web toward the deepest gravitational wells, where it can be heated to tens of millions of degrees Celsius and form a diffuse high-energy atmosphere that fills the space between the galaxies. Inside such an atmosphere, galaxies move through a thin but energetic medium, and their own gas can be stripped away by a process called ram pressure, as they orbit through the cluster or group, changing their ability to form new stars and gradually transforming their appearance over long time scales. Observations in visible light, high-energy radiation and radio waves together provide a layered view of these environments. Visible light shows the stars in the galaxies. High-energy radiation traces the hot intra-cluster or intra-group gas, and radio observations reveal jets and lobes associated with central active galaxies, which are powered by matter falling into very massive central objects. On large scales, the positions of galaxy groups and clusters in the Centaurus direction line up along several main filaments that curve across hundreds of millions of light-years, and these structures are themselves part of even larger supercluster complexes that extend well beyond the patch of sky that carries the name Centaurus. Within this web, the typical separation between rich clusters is measured in many tens of millions of light-years, while the filaments between them have widths of a few millions of light-years, and within the filaments smaller knots mark the positions of modest galaxy groups whose combined gravity is enough to keep their member galaxies bound together against the general expansion of the universe. The overall picture that emerges from these observations is that the Centaurus region is not defined by a single object or system, but by the way matter has settled into a connected network with galaxy groups, clusters, and their hot gas halos sitting like beads along the filaments of the cosmic web, each one a local deepening of the gravitational landscape within the larger scale structure of the universe at the present epoch. To understand why such a web exists at all, astronomers connect the present-day map of galaxies with measurements of the very early universe, when tiny variations in density are imprinted on the cosmic microwave background and serve as the seeds from which filaments and clusters grow under the pull of gravity. Regions that begin slightly denser than average attract more matter, and over billions of years they evolve into the filaments and knots seen today, while under-dense regions lose matter and widen into the large voids that open between the main structures, dark energy. The form of energy associated with the accelerated expansion of the universe stretches space on the largest scales and gradually slows the rate at which new large structures can form, so that by the present epoch, the pattern of the cosmic web in the Centaurus direction is largely in place with its main filaments, clusters, and groups established. Within this framework, any individual galaxy group in the Centaurus region can be thought of as one node in a much larger network linked by streams of infalling matter to neighbouring systems and to the deep potential wells of richer clusters and the properties of its galaxies. Their star formation histories and their gas content are all shaped over time by their position in this web. As a result, the wide field that appears at first glance to be a simple scattering of faint smudges on the sky is in fact a cross-section through a vast three-dimensional structure where every group and cluster is connected to others by the threads of the cosmic web that spans the observable universe. In the cosmic web described before, individual galaxy groups and clusters appear as distinct knots where gravity has drawn together both visible matter and dark matter, and one such knot in the direction of the constellation Centaurus is known as the NGC 88 group. Astronomers identify a galaxy group by measuring the positions and line-of-sight velocities of many galaxies on the sky, and finding a set that share similar distances and move within a limited range of speeds relative to the expansion of the universe. And for this particular group, those measurements point to a system located a little over 200 million light-years away. Within this group there are roughly 12 known member galaxies, including several catalogued systems that range from modest spirals and lenticular galaxies to much more massive elliptical galaxies, all of them orbiting together within a common gravitational field. The group is often listed under a numerical label in catalogues of nearby galaxy associations, but physically it is best understood as a bound collection of galaxies whose motions reveal that they share a deep potential, well dominated by dark matter, rather than by the visible stars and gas alone. At the heart of this group sits a giant elliptical galaxy, NGC 5419, whose luminosity and central position make it the brightest and most massive member, and around it the smaller galaxies move on elongated orbits, falling in toward the centre and sometimes passing close before moving back out again to larger radii. Over billions of years, repeated close passages and mergers between group members contribute to the growth of the central galaxy, while tidal forces strip stars and gas from satellites and spread them into faint streams and a diffuse intra-group component that is difficult to see in shallow images but can be detected with deeper observations. Measurements of the projected separations between the brighter galaxies and of their velocities along the line of sight allow astronomers to estimate the total mass required to keep the system bound, and these mass estimates routinely exceed the combined mass of the stars in the individual galaxies by a large factor, pointing to an extended halo of dark matter that envelops the entire group. Embedded within the same large-scale environment is a somewhat richer system that is classified as a poor cluster of galaxies known as Abell S 0753, for which NGC 5419 again appears as the central dominant galaxy. A poor cluster contains more galaxies and hot gas than a simple group, but fewer than the richest clusters. It fills a region of space several million light-years across, and includes dozens rather than hundreds of galaxies, along with a substantial amount of diffuse high-temperature gas that emits strongly in high-energy radiation. In such a cluster, the bright central elliptical galaxy often sits near the bottom of the gravitational potential well, and its position is not accidental, but the result of past accretion events in which it has grown by cannibalizing smaller companions and by gathering material that has been stripped from other galaxies by tidal forces and by their motion through the intracluster medium. The intracluster medium is a very thin hot plasma, far less dense than the best vacuums achieved in laboratories on Earth, but extended over large volumes, it contains more mass than the combined cold gas inside all the galaxies of the cluster, and its pressure and temperature can be inferred from high-energy observations that reveal a roughly smooth atmosphere centered on NGC 5419. In the Abell S 0753 system, the galaxies move against this hot background, with typical speeds of hundreds to more than 1,000 kilometers per second, their orbits drawn out by the combined gravitational pull of dark matter, hot gas, and the massive galaxies themselves, and the density of galaxies in the inner region is high enough that interactions and close flybys are common over cosmic timescales. Each galaxy carries with it its own star's gas and dark matter subhalo, and so the dynamical state of the group and cluster environment is complex, with smaller subgroups, sometimes falling in along filaments and gradually being assimilated into the main potential well. When such a subgroup enters the cluster, its member galaxies can be seen as a small association with a coherent motion, relative to the cluster average, and shocks and cold fronts may form in the hot gas as the intracluster medium responds to the new infall, although in the present context the detailed gas structures of Abell S 0753 remain less well mapped than in some nearby richer clusters. Observations that combine visible light imaging spectroscopy of galaxy velocities and high-energy data from space-based observatories together build up a consistent picture in which the NGC 5488 group and the Abell S 0753 cluster are stages of the same gravitationally bound environment, with NGC 5419 occupying the central position in both frames. In that picture, the inner region of the group and cluster is dominated by the bright, smooth light of NGC 5419, while farther out the ski is sprinkled with smaller galaxies of various shapes and brightnesses, each following its own path around the common center of mass. The gravitational potential of this environment not only shapes the motions of galaxies, but also influences their internal evolution. Gas-rich spirals that fall in toward the center can lose their cold gas reservoirs to ram pressure stripping as they move through the hot intracluster medium, and over time their star formation rates decline, nudging the overall galaxy population of the group and cluster toward earlier types, such as lenticular and elliptical systems. In the present epoch, the NGC 5488 group and Abel S0753 cluster therefore represent a mature environment in which the central giant elliptical, NGC 5419, already dominates the light and mass budget, and where the surrounding galaxies and hot gas contribute to a layered structure extending from the core of the cluster out into the lower density regions that connect back into the filaments of the wider cosmic web. Within this extended environment, the central galaxy does not stand alone but is embedded in a dynamic context, whose scale spans many millions of light years, and understanding NGC 5415 on smaller scales requires first appreciating how deeply it is tied to the group and cluster that form the immediate setting for all of its later internal structure. In many galaxy groups and clusters, the brightest and most massive member is a huge elliptical galaxy, a system whose stars are arranged in a smooth, roughly ellipsoidal distribution rather than in a thin rotating disk with spiral arms, and whose light is dominated by old reddish stars that formed long ago. An elliptical galaxy can be understood as a collection of stars, dark matter, and hot gas held together by gravity. But unlike a spiral galaxy, it usually shows little or no sign of ongoing large-scale star formation, because most of its cold gas has been used up, heated, or removed by past events in its environment. The light profile of such a galaxy, which describes how brightness changes with distance from the center, typically falls steeply from the central regions outward and over a wide range of radii. This profile can be described by simple mathematical forms reflecting the way orbits of many stars add together to produce a smooth glow. The most massive elliptical galaxies in groups and clusters are often called brightest group galaxies or brightest cluster galaxies, and they stand out not only because they are luminous, but also because they lie close to the dynamical center of their host system, the point around which the overall mass distribution is roughly balanced. In images, these galaxies appear as large diffuse ovals with only subtle structure, often extending far beyond the radii at which the smaller companion galaxies fade into the background sky, and deep exposures reveal that their outer halos can merge almost seamlessly into the faint intragroup or intracluster light made of stars that no longer clearly belong to any single galaxy. Kinematic studies which measure the line of sight velocities of many stars or of the integrated light at different positions show that these giant ellipticals are supported not primarily by ordered rotation, but by random motions, and the typical speed of these random stellar motions, known as the velocity dispersion, can reach several hundreds of kilometers per second. A high velocity dispersion indicates a deep gravitational potential well, which in turn points to a very large total mass in stars and dark matter, and in the most massive systems that mass can add up to several trillion times the mass of the Sun when the extended halo is included, the colours of these galaxies are usually redder than those of star-forming spirals reflecting a stellar population made of older, cooler stars. Astronomers refer to this as a red and dead population, meaning that most of the short-lived blue stars have already evolved away, and that current star formation contributes only weakly to the total light. The prevailing picture from both observations and simulations is that brightest group and cluster galaxies grow over cosmic time through a mixture of early rapid star formation in smaller progenitors and later merging and accretion events in which they absorb other galaxies that fall into the same potential well. Major mergers between galaxies of comparable mass can scramble stellar orbits and help build up a smooth elliptical remnant, while minor mergers in which a massive galaxy accretes much smaller satellites tend to contribute stars to the outer halo and can produce long, faint streams that eventually dissolve into the background light. In dense environments such as the core of a group or cluster, These processes are especially efficient because the high number density of galaxies and the shared dark matter halo increase the chance of close encounters and slow the relative motions enough that gravitational interactions can lead to mergers rather than simple flybys. NGC 54419 is one of these central massive ellipticals, and in the combined group and cluster environment around it, it plays the role of brightest group and brightest cluster galaxy, sitting near the center of the potential well defined by the surrounding dark matter and hot gas. Its smooth light distribution and high luminosity place it among the more massive elliptical galaxies in the nearby universe, and observations of its stellar kinematics indicate a large velocity dispersion consistent with a deep gravitational potential. At large, radii, the outer envelope of NGC 54419, blends into the intragroup and intracluster light, making it difficult to define a sharp edge to the galaxy, and the distinction between the galaxy and its environment becomes partly a matter of convention based on surface brightness thresholds. Inside those outer regions, the main body of the galaxy follows the general pattern seen in other giant ellipticals, a smooth decrease of brightness with radius red colours indicating an old stellar population and stellar motions that are largely random rather than highly ordered around a single rotation axis. The dark matter halo that surrounds NGC 5419 and its group provides most of the mass at large distances from the centre, while the stars dominate the visible light in the inner regions, and together they create a gravitational field that controls the orbits of both stars and satellite galaxies. In this sense, NGC 5419 fits naturally into the broader class of brightest, group and cluster galaxies acting as a central hub that has grown through many past interactions and mergers and that now shapes the dynamical state of its surrounding environment. Comparisons with other well-studied brightest cluster galaxies show that NGC 5419 shares many of their broad properties, such as a large effective radius that encloses half of its light an extended low surface brightness envelope, and a central region in which the stellar density rises well above that of any neighbouring galaxy. In clustering studies, central galaxies like NGC 5419 are often used as markers of the locations of massive dark matter halos, because their positions trace the centres of group and cluster scale potentials, and their luminosities correlate with the total mass of those halos. In the broader context of galaxy evolution, such systems illustrate how environment influences morphology and star formation history, demonstrating that in the densest regions of the cosmic web, the end products of hierarchical growth are giant ellipticals that dominate their surroundings in both mass and light. At the centre of its group and poor cluster environment, NGC 5419 appears in deep images as a large smooth ellipse of light, set against the background of more distant galaxies, and the foreground stars of the Milky Way, a single galaxy that nevertheless occupies a substantial patch of the sky. Distance measurements based on its recession velocity and on more detailed methods place it at roughly 200 million light-years from Earth, far beyond the stars of the Milky Way yet still in the nearby universe on cosmological scales, and at that distance even a modest angular span on the sky translates into a very large physical size. The main body of NGC 5419 extends over more than 100,000 light-years from one side to the other, when its faintest measurable outskirts are included, and its outer halo reaches even farther into space, blending gradually into the intragroup and intracluster light that surrounds the galaxy. In projection on the sky, its isophotes. The contours of constant surface brightness are close to elliptical, with only a mild flattening that indicates a three-dimensional shape somewhere between a sphere and a more elongated ellipsoid, and the orientation of this apparent ellipse defines a major and minor axis for describing positions within the galaxy. Imaging in visible and near-infrared light shows that the colour of NGC 5419 is uniformly quite red, with only gentle gradients that become slightly bluer toward the outskirts, a pattern that suggests a dominant population of old cool stars in the inner regions and a modest contribution from somewhat younger stars at larger radii. The overall surface brightness profile, which describes how the intensity of light falls off with distance from the centre, declines steadily from a bright core through the main body into the extended halo, and over most of its radial range, this profile can be approximated by the same family of mathematical functions that describe many other elliptical galaxies of high mass. When astronomers integrate this profile over the projected area of the galaxy, they infer a very high total luminosity, equivalent to several hundreds of billions of suns, and when they combine that luminosity with estimates of the typical mass carried by the kinds of old stars that dominate the light, they obtain a stellar mass that reaches into the range of many hundreds of billions of solar masses. This large stellar mass means that NGC 5419 is not only the brightest member of its group and poor cluster, but also one of the more massive galaxies in the nearby universe, and its gravitational attraction plays a central role in the dynamics of the surrounding galaxies and hot gas. In addition to the stars, there is evidence for a modest amount of diffuse hot gas associated with the galaxy itself, particularly in its central regions where a shallow atmosphere blends into the larger-scale intracluster medium. This gas emits primarily in high-energy radiation and is detected with space-based observatories rather than with ground-based telescopes. At optical wavelengths, where the bulk of the stellar light is recorded, the galaxy is remarkably featureless. On large scales, there are no clearly defined spiral arms, no large dust lanes crossing the main body, and no strong patches of ongoing star formation that would stand out as bright blue knots, features more typical of gas-rich spiral or irregular galaxies. Instead, the impression is one of a smooth, almost serene glow whose brightness is highest near the centre and gradually tapers off with increasing radius, with only subtle changes in the ellipticity and position angle as one moves outward, signatures of the complex assembly history of the galaxy, but not strong enough to break the overall symmetry. Deep exposures can reveal a few faint shells, ripples, or tidal streams in the outer halo relics of past interactions, and mergers with smaller galaxies that have been partially digested by NGC 5419. But these features carry only a small fraction of the total light, and do not disrupt the basic elliptical form. The galaxy's light is dominated by stars of low and intermediate mass that shine steadily for billions of years, and the lack of strong emission from hot young stars or from large reservoirs of cold gas suggest that current star formation in NGC 5419 is low, consistent with its classification as a quiescent elliptical system. Kinematic studies of the integrated stellar light, while focused more closely in later analyses, indicate that on global scales the random motions of stars dominate over ordered rotation, and this dynamical structure helps to maintain the broad spheroidal shape implied by the photometry. The dark matter halo in which NGC 5419 is embedded extends far beyond the visible stars, but within the inner regions that define the luminous galaxy, the stellar mass is a major contributor to the gravitational potential, so that the light distribution and the mass distribution are closely linked. Across its full extent from the bright inner body to the faint outer halo, NGC 5419 therefore presents itself as a massive red and smooth elliptical galaxy whose global form and scale have been built up over billions of years through processes that operate within the dense environment of its group and poor cluster, setting the stage for the more detailed structures that appear only when attention turns inward to its inner kiloparsecs and eventual central core. From the standpoint of classification schemes that organize galaxies by their appearance and stellar content, NGC 5419 resides firmly among the most massive early type systems, and its large effective radius, which encloses roughly half of the total light, underlines how extended its stellar body is compared with more ordinary galaxies. When maps of surface brightness are examined in detail, they show that isophotes at intermediate radii are slightly boxy, rather than perfectly elliptical, a common feature in very massive ellipticals that reflects the mix of different stellar orbit families contributing to the global figure. Observations made at different wavelengths confirm the general picture that emerges from visible light alone in the near-infrared, where cooler stars contribute strongly. The galaxy looks even smoother and more regular, while in the ultraviolet it appears relatively faint, consistent with the low rate of recent star formation. Radio observations detect weak emission, associated either with an active nucleus or with past episodes of nuclear activity, but on the scale of the whole galaxy, these signals add only a minor layer to the dominant stellar glow. Taken together, these multi-wavelength views reinforce the idea that NGC 5419 is a mature, massive elliptical galaxy, whose global appearance is stable on human timescales. A system whose large size and smooth light distribution reflect a long history of assembly and relaxation within the deep gravitational well at the center of its group and poor cluster. Far from the bright central regions of NGC 5419, the galaxy extends into a realm where the surface brightness is so low that only deep and careful imaging can reveal that starlight is still present, forming an extended stellar halo and outskirts that grade almost imperceptibly into the wider intragroup and intracluster environment. In ordinary exposures, the galaxy seems to end where the main body fades into the background, but longer integrations and sensitive detectors show that its light continues much farther, wrapping the central regions in a very diffuse envelope of stars whose glow is only slightly above the sky. This halo is not a sharp structure with a clear border. Instead, it is a gradual continuation of the galaxy, where the density of stars falls steadily with radius, and the contrast against the background weakens until it becomes difficult to decide where the galaxy truly stops and the surrounding space begins. The stars in these outskirts are typically old and of low mass, similar to those that dominate the main body, but their distribution carries special information about the assembly history of the system, because the outer halo is particularly sensitive to accretion events and tidal stripping that have taken place over billions of years. When smaller galaxies fall into the group and pass close to NGC 5419, gravitational tides can pull stars out of them and deposit those stars into extended stream shells and plumes that eventually disperse and blend into the halo, and traces of such features can sometimes be seen in very deep images as faint arcs and patches around the main galaxy. Even when these individual structures are no longer distinct, the accumulated effect of many past interactions leaves an imprint on the shape and radial profile of the halo, which may become more elongated, more asymmetric, or more extended along preferred directions associated with the orbits of accreted satellites. In the outskirts, the light that is still bound to NGC 5419 begins to overlap with the intragroup and intracluster light, which is made of stars that no longer belong cleanly to any single galaxy, but instead orbit in the broader gravitational field of the group and cluster. This intragroup light can arise when stars are stripped from galaxies during close encounters, or when disrupted satellites are stretched so far that their remnants are no longer recognizable as separate systems, and in the central regions of a group or cluster, it often forms a vast, extremely low surface brightness envelope, centered roughly on the brightest cluster galaxy. For NGC 5419, sitting at the center of its group and poor cluster environment, the outer halo therefore does not end abruptly. Rather, it fades into a diffuse sea of such intragroup stars, and any attempt to separate the halo of the galaxy from the more general intracluster component is necessarily somewhat conventional based on how the surface brightness profile is modeled and where a threshold is chosen. The colors of the halo and outskirts when measured tend to be similar to, or slightly bluer than those of the inner body, indicating a mix of stellar populations that may include more metal, poor stars contributed by small disrupted satellites, along with the older stars originally formed in the main galaxy. Individual stellar traces such as planetary nebulae and bright red giant stars can sometimes be detected in these regions with specialized techniques, and their spatial distribution and motions offer a way to map how the halo transitions into the intragroup light, showing that the influence of the central galaxy extends to large radii. Globular clusters, which are dense old clusters of stars, also populate the outskirts. In massive ellipticals and brightest cluster galaxies, the system of globular clusters can reach far beyond the effective radius of the stellar light, and counts of these clusters around NGC 5419 indicate that its halo is rich in such objects. These globular clusters move in the combined gravitational potential of the galaxy and its dark matter halo, and their velocities provide clues to the mass distribution on large scales, complementing what can be learned from the smooth starlight alone. Kinematic studies show that in the outer parts of massive ellipticals the stellar motions remain largely pressure-supported, meaning that random motions dominate over ordered rotation, and this is expected to hold in the outskirts of NGC 5419 as well, where stars and globular clusters move along complex three-dimensional orbits, rather than circling in a thin rotating disk. The dark matter halo becomes increasingly important at these large radii, contributing most of the gravitational pull that keeps stars, clusters, and strip material bound to the central region of the group and poor cluster. And as a result, the outer halo of NGC 5419 is not just an extended stellar component, but also a tracer of the underlying dark matter distribution. In the outskirts, the gravitational influence of the central galaxy begins to overlap with that of the surrounding group and cluster, so that stars and globular clusters there respond to the combined mass of NGC 5419, its dark halo, the intragroup medium and nearby galaxies. This shared potential well explains why some of the light at very low surface brightness does not strictly belong to any one object, but instead forms a common envelope around the central galaxy and its immediate environment. Because the light levels are so faint, mapping these regions in detail is difficult, and much of what is known about the halos of galaxies like NGC 5419 comes from deep, carefully processed images that push close to the limits of what current instruments can achieve. Yet even with these observational challenges, the broad picture that emerges is that the outer halo and outskirts of NGC 5419 represent a quiet but important zone, where the history of past mergers and accretion events is written in diffuse structures, where the boundary between galaxy and cluster is blurred, and where stars move under the combined influence of the central mass concentration and the broader group and cluster halo. In this sense, the extended stellar halo is not simply an addendum to the main galaxy, but an integral part of the system connecting the inner brighter regions of NGC 5419 to the wider environment of the NGC 5488 group and ABEL S0753, and providing the outermost stellar layer that encloses all of the more central structures yet to be examined. Surrounding the bright stellar body and faint outskirts of NGC 5419 is an even larger and more massive component that does not shine at any wavelength. The dark matter halo, an extended nearly invisible structure whose gravity shapes the motions of stars, globular clusters, satellite galaxies and hot gas throughout the group and poor cluster. Dark matter is inferred because the visible matter alone in the form of stars and gas cannot account for the observed speeds at which objects move within and around galaxies. If only the luminous mass were present, many stars and satellites would be moving too fast to remain bound. In NGC 549 and its environment, the evidence for such an extended halo comes from several lines of observation that all point to a deep gravitational potential, whose mass far exceeds the mass traced directly by starlight. One of these lines is the velocity dispersion of stars within the galaxy, which remains high even at large radii, indicating that the total mass enclosed grows more rapidly than the stellar light alone would suggest. Another is the pattern of velocities of satellite galaxies in the NGC 5488 group and the Abell S0753 Poor cluster, where the speeds of the satellites relative to the group or cluster center are large enough that a substantial dark matter component is required to keep the system gravitationally bound. A third is the presence of hot gas that fills the space between galaxies in the group and cluster, forming a diffuse intragroup and intracluster medium that is heated to tens of millions of degrees Celsius and emits strongly and high-energy radiation. The pressure support of this gas depends on the depth of the gravitational potential, and measurements of its temperature and density profile imply a total mass dominated by dark matter. In combination, these clues show that the luminous parts of NGC 5419, impressive though they are, sit deep inside a much larger halo of dark matter that extends well beyond the visible galaxy and out into the broader group and cluster environment. The dark matter halo is thought to be roughly spheroidal in shape, with a density that is highest near the center and falls off gradually with distance, and simulations suggest that its inner regions are relatively smooth, while its outer parts can contain substructure in the form of smaller dark matter clumps associated with satellite galaxies and remnants of past mergers. Within this halo, the stars of NGC 54119 move on orbits that respond to the combined gravitational pull of both dark and luminous matter, and the same is true for the globular clusters and planetary nebulae that inhabit the outer regions. The fact that the velocity dispersion remains high, even where the surface brightness of starlight becomes very low, indicates that dark matter provides a substantial portion of the total mass at those radii, raising the escape speed and allowing stars to move quickly without leaving the system. On still larger scales, the satellite galaxies that make up the rest of the NGC 5488 group and the Abell S0753 Poor cluster trace the outer parts of the same potential well, and their orbits form a dynamical laboratory for estimating the mass and extent of the halo. Astronomers observe the line-of-sight velocities of many satellites and model their distribution under the assumption that they are bound to the common halo. The resulting mass estimates again show that dark matter dominates the total. The hot intragroup and intracluster gas provides an independent check on this picture, because the gas is in approximate hydrostatic equilibrium, meaning that pressure gradients balance gravitational forces on average. Its temperature and density profiles encode information about the underlying potential. When these profiles are matched by models that include gravity from both dark matter and baryonic matter, they typically require a massive extended dark halo, whose center coincides with the position of the brightest group or cluster galaxy, NGC 5419. Thus, while the dark matter itself does not emit light, its presence is written clearly into the way visible components arrange themselves and move throughout the system. The depth of the gravitational potential well associated with this halo has several important consequences for the structure and evolution of NGC 5419 and its environment. It sets the typical speeds of stars and satellites, which in turn influence the efficiency of galaxy mergers and tidal stripping. When relative velocities are moderate, and the potential is deep, slow encounters, and captures are more likely encouraging the growth of the central galaxy over long timescales. It helps to confine the hot intragroup and intracluster gas, preventing it from escaping into intergalactic space, and allowing it to form a stable atmosphere that can slowly cool and in some regions condense, although in many massive systems the cooling is balanced or offset by heating from central active galaxies. It also defines a region known as the virial radius, within which the system can be approximated as gravitationally bound and in quasi-equilibrium, though the exact boundary is a model-dependent concept rather than a sharply observable edge. Within this radius, the motions of stars and galaxies are largely dictated by the static pull of the halo, rather than by the overall expansion of the universe. For NGC 5419, the dark matter halo therefore provides the scaffolding on which all of the visible structures sit: the main stellar body, the extended halo and outskirts, the distribution of globular clusters, and the orbits of satellite galaxies are all embedded within and constrained by this unseen component. At smaller radii, where the stellar mass becomes significant, the potential is shaped by both stars and dark matter, but even there the underlying halo contributes a substantial fraction of the total gravitational pull. At larger radii, far beyond the bright core and main body, the dark halo dominates almost completely, guiding the paths of light traces and determining how the group and poor cluster as a whole move within the surrounding cosmic web. Because dark matter interacts primarily through gravity and not through electromagnetic forces, it does not clump on very small scales in the same way as gas and stars. Instead, it forms a relatively smooth background that responds only slowly to local processes such as star formation or feedback from active galactic nuclei. This smoothness helps explain why the large-scale gravitational field of NGC 5419 and its halo changes only gradually over cosmic time, even though individual galaxies within the group may merge or be disrupted. Over the billions of years during which NGC 5419 has assembled, its dark matter halo has grown through the accretion of smaller halos and the infall of matter along filaments of the cosmic web, and by the present epoch it has become a massive relaxed structure whose central regions are well described by simple density profiles, and whose outer parts merge into the larger scale environment. In this way, the dark matter halo and the deep potential it creates provide the backdrop for all subsequent layers of structure inside the galaxy, from the bright stellar body to the inner regions that lie far closer to the center, and they determine the basic dynamical conditions under which stars and gas move throughout the NGC 5419 system. Between the faint outskirts of NGC 5419 and the much denser inner regions lies the main stellar body of the galaxy, the broad swath of light where most of its stars reside, and where the smooth appearance of a giant elliptical becomes most evident. In this zone, extending over many tens of thousands of light years, the surface brightness is high enough that the galaxy dominates the local sky, yet low enough that individual features, if present, would stand out against the background. Observations show, however, that on these scales, NGC 5419 remains remarkably regular, with isophotes that are gently elliptical and with only small twists in orientation as one moves inward. The light at these radii is produced by a vast population of stars that formed long ago and their combined glow gives the galaxy its characteristic reddish color. Spectra taken across the face of NGC 54119 indicate that the stellar populations in this outer body are old, typically many billions of years in age, and enriched in heavy elements compared with primitive gas, reflecting a long history of star formation and chemical recycling that took place mostly in the early stages of the galaxy's assembly. The colours change only slowly, with radius becoming a little bluer farther out, which suggests that the outer parts contain a somewhat larger fraction of metal. Poor stars possibly contributed by smaller galaxies that were accreted and dispersed into the main body over time. In this region, the surface brightness profile declines smoothly with distance from the centre, following the general pattern seen in many massive ellipticals, and when mapped carefully it reveals no strong breaks or rings that would indicate disks or other large-scale substructures. To understand how the stars move in the main body, astronomers measure the broadening and shifts of absorption lines in integrated spectra at many positions across the galaxy. These measurements show that the typical random speed of stars, the quantity known as the velocity dispersion, is very high, reaching several hundreds of kilometers per second over a wide range of radii. A high velocity dispersion means that stars orbit in many different directions rather than streaming together around a single axis, and that the gravitational potential is deep enough to keep these fast-moving stars gravitationally bound. Superimposed on these random motions is a slower ordered rotation of the stellar body. When the line of sight velocities are plotted along the apparent major axis of the galaxy, a gentle gradient appears on one side. The stars are on average slightly more redshifted, meaning they move away along the line of sight, and on the other side they are slightly more blue-shifted, meaning they move toward along the line of sight. This pattern indicates that the outer stellar body rotates, but the net rotation is modest compared with the overall velocity dispersion. The galaxy is therefore described as a slow rotator, a system in which random motions provide most of the support against gravity, and rotation plays a secondary role. Two-dimensional maps of the stellar kinematics obtained with modern integral field spectrographs confirm this picture for galaxies like NGC 54119. Contours of constant velocity dispersion remain high and fairly round in the main body, while the rotation field shows only gentle large-scale variation. In a fast-rotating galaxy such as a typical spiral, the rotation speed can rival or exceed the velocity dispersion, and the stars are concentrated in a thin disk. In NGC 54119 the opposite is true, and the stars fill a thick three-dimensional region in which many different orbit families contribute to the overall shape. Some stars follow box-like orbits that carry them to large distances above and below the main apparent plane, while others occupy more elongated or tube-like paths that loop around the center. The blend of these orbits set by the galaxy's formation history and the overall shape of its potential gives rise to the observed flattening and the subtle boxiness of the isophotes, without producing clear disk structures or sharp features. The density of stars in the main body is high enough that the space between them on average is still small compared with the vast separations in the outer halo, yet they are far apart on human scales, separated by distances of light years, and collisions between stars are exceedingly rare. Instead, each star follows its own path around the center of mass, perturbed only slowly over time by the collective gravitational field of its neighbors and by any global changes in the potential due to continuing accretion events in the wider group and cluster. The stellar populations in this region also encode information about the build-up of the galaxy. Detailed spectral analysis suggests that the stars in the main body of a massive elliptical like NGC 54119 formed rapidly at early times over intervals shorter than a few billion years from gas that had already been enriched by previous generations of stars. This early intense episode of star formation would have produced many massive stars that lived brief lives and ended as core collapse supernovae, seeding the gas with additional heavy elements and contributing to the chemical patterns now seen in the long-lived stars that dominate the light. Later mergers with other galaxies, particularly minor mergers with smaller systems, would have added stars that formed under somewhat different conditions, altering the gradients in age and metallicity across the main body. In NGC 5419, as in other brightest group and cluster galaxies, these later additions appear to have built up the outer parts more than the inner ones, consistent with the slight color gradients, and with models of hierarchical growth. Within the main stellar body, dust is scarce. Deep images show no large coherent dust lanes, like those seen in some central ellipticals that have recently accreted gas-rich companions. Any dust that is present is confined to very small scales or very low surface brightness structures that do not strongly affect the global light distribution. This lack of dust and the absence of strong emission from young hot stars both reinforce the idea that ongoing star formation is minimal. The interstellar medium in this region is dominated instead by very low density hot gas, if any, and by the old stellar population itself. The smoothness of the light and the stability of the global kinematics suggest that the main body of NGC 54119 has had time to relax dynamically, meaning that the random motions of stars have redistributed them into a configuration that changes only slowly under the influence of the large-scale potential. Small perturbations from minor interactions or from the falling in of distant satellites can still occur, but they add gentle ripples rather than dramatic distortions. Embedded within this broad, slowly rotating high dispersion, stellar C-globular clusters appear as unresolved points of light that orbit along with the stars, while planetary nebulae, briefly luminous shells around dying stars, serve as additional traces of the gravitational field. Their measured velocities match the trends seen in the integrated light, confirming that the slow rotation and strong random motions are not artifacts of the measurement technique, but genuine properties of the stellar system. In this way, the outer stellar body of NGC 549, thicker and more dynamically hot than any stellar disk, forms a stable and luminous layer that connects the diffuse outskirts and halo to the denser inner regions and shows in its motions and populations the imprint of the galaxy's long formation history within the deep potential well defined by its own mass and the surrounding dark matter halo. Moving inward from the broad main stellar body of NGC 5419, the smooth decline of surface brightness continues until, on scales of only a few thousands of light years from the center, a more subtle change begins to appear in the way the light is distributed. In many less massive elliptical galaxies, the central regions show an increasingly steep rise in brightness, toward the very center following the same functional form that describes the outer profile, or even becoming more sharply peaked. But in NGC 54119, and in other very massive ellipticals, the inner profile instead becomes shallower, forming what astronomers call a depleted stellar core. This term refers to a central zone where the surface brightness is lower than would be expected if the steeper outer profile simply continued all the way inward, implying that relative to that extrapolation, stars are missing from the innermost region. Approaching this core from larger radii, one first crosses the part of the galaxy where the projected brightness still roughly follows the outer law, and where the isophotes remain gently elliptical, and the kinematic properties still resemble those of the main body described earlier, with high velocity dispersion and modest rotation. As the radius decreases to the inner few kiloparsecs, careful fitting of the light profile reveals a characteristic scale at which the slope changes from steep to shallow. Beyond this break radius inward toward the center, the surface brightness no longer rises as quickly, and when compared with a model that extends the outer profile, the inner region appears underluminous by an amount that corresponds to a very large number of stars. To identify and quantify this behavior, astronomers analyze high-resolution images obtained with space-based telescopes and large ground-based facilities equipped with excellent seeing or adaptive optics. They extract radial profiles of surface brightness along different directions and fit them with functions that combine an outer component representing the bulk of the galaxy with an inner component that accounts for the flattened core. For NGC 514, these analyses show that the depleted core is large even by the standards of massive ellipticals extending over a region that spans many hundreds of light-years across, and that the deficit of light relative to an inward extrapolation of the outer profile is substantial. In simple visual terms, this does not mean that the center of the galaxy is dark or empty. The core is still filled with stars and remains one of the brightest parts of the galaxy when viewed on the sky. The depletion is a relative concept defined with respect to what the luminosity profile would look like if the trend from larger radii continued unchanged. When that hypothetical profile is drawn on the same plot as the actual observations, the difference between them in the inner region corresponds to the missing starlight. Approaching the core region in this way, the galaxy therefore appears to transition from a regime where the structural properties resemble those of a more ordinary elliptical, to one where the central structure carries clear signatures of processes that operate only in very massive systems. The isophotes near the break radius often show small changes in shape, becoming slightly rounder or developing mild boxiness or diskiness. But in NGC 5414, the overall symmetry remains high, and the core blends smoothly into the surrounding main body without sharp edges or obvious substructures at this scale. Photometrically, the central color gradient also tends to flatten in the core region, which suggests that the mix of stellar populations there is relatively uniform compared with the stronger gradients that may exist farther out. This is consistent with the idea that stars in the core have been redistributed over time by dynamical processes that mix orbits and smooth out small-scale variations. In the inner few kiloparsecs where the depleted core resides, the density of stars in 3 dimensions is still extremely high, but compared with an extrapolated cusp it is lower, and the corresponding change in the gravitational potential is subtle rather than dramatic. Stars entering this region from larger radii do not encounter a physical boundary or abrupt barrier. Instead, their orbits gradually carry them into a slightly less crowded central zone than might otherwise be expected, and their motions respond to a potential that reflects the altered density profile. Kinematic studies that probe these radii show hints of changes in the pattern of stellar motions as the core is approached. The rotation curve can begin to shift, and the velocity dispersion profile can show a plateau or gentle central rise features that indicate a distinct dynamical environment compared with the outer body, even though the differences are modest when projected along the line of sight. The core region, therefore, is not just a photometric feature, but a zone in which the interplay between stellar orbits and the central mass distribution has produced a configuration that differs from that of galaxies without such cores. In the context of galaxy evolution, depleted stellar cores in massive ellipticals are widely interpreted as the outcome of past mergers between large galaxies, whose central regions contained very massive compact objects. During such events, the central objects from the progenitor galaxies sink toward the common center under the influence of dynamical friction, forming a bound pair that interacts gravitationally with the surrounding stars. Through repeated 3-body encounters, stars that pass near the pair can be accelerated and ejected to larger radii, or even out of the galaxy, carrying away energy and angular momentum and causing the central stellar density to drop. The result, after many such interactions and over long timescales, is a central region depleted of stars relative to the inward continuation of the outer profile. In NGC 5419, the size and depth of the depleted core suggest that the central regions have experienced one or more such major events in their past, and that the current structure of the inner light profile still carries the imprint of that dynamical history. As the view narrows to those inner few kiloparsecs, attention naturally focuses on this core, both as a structural boundary between the main body and the very centre, and as a record of the processes that have shaped the heart of this massive galaxy within its group and poor cluster environment. Within the inner few thousands of light-years of NGC 5419, the change in the surface brightness profile that marks the depleted stellar core can be described more precisely, and this central structure becomes a quantitative record of how many stars have been removed from the innermost region. Astronomers model the radial distribution of light in massive elliptical galaxies with a family of functions that capture both the steep outer decline and any flatter behavior near the center. For galaxies without depleted cores, a single mathematical law, often called a Sérsic profile, is usually sufficient to describe how brightness falls off from the center to large radii. In core galaxies like NGC 5419, however, this simple form fails in the inner part because the real profile becomes shallower than the inward continuation of the outer law. To represent this behavior, observers use a modified form called a core Sérsic profile, in which the outer region still follows the usual steep curve, but the inner region transitions to a flatter slope inside a characteristic break radius. That break radius marks the approximate boundary of the depleted core and can be measured by fitting high-resolution images of the galaxy's central light distribution. In NGC 5419, space-based and large ground-based observations show that the break occurs at an angular scale of about 1.5 arcseconds from the center. At the distance of the galaxy, this angle corresponds to a physical radius of several hundred parsecs, which is roughly on the order of 1,300 light-years, making the depleted core exceptionally large, even compared with those of other massive elliptical galaxies. Inside this radius, the observed surface brightness rises toward the center, much more slowly than the outer profile would predict, and when astronomers extrapolate the outer Sérsic law inward and compare it with the actual measurements, they find that the inner regions contain less starlight than expected. The difference between the extrapolated and observed light integrated over the area of the core is called the missing light, or light deficit. It does not represent an actual dark cavity, because the core is still bright and densely populated with stars. Instead, it is a way of expressing how much stellar luminosity is lacking relative to a hypothetical galaxy with the same outer structure but without a depleted center. To convert this light deficit into a stellar mass deficit, one multiplies by the mass to light ratio of the stellar population, which is derived from dynamical modeling and from analyses of the stellar spectra. For NGC 5419, this procedure indicates that the stellar mass missing from the core is on the order of tens of billions of times the mass of the Sun, a deficit comparable to a few times the mass of the very massive central object or objects inferred from the galaxy's kinematics. This ratio between mass deficit and central mass is similar to the values found in other core ellipticals and matches predictions from theoretical models in which repeated gravitational encounters with a central massive pair eject stars from the inner region. In those models, when two massive galaxies merge without much cold gas, their central compact objects spiral toward the new common center under the influence of dynamical friction, forming a bound pair. Stars whose orbits bring them close to this pair can be scattered onto larger, more weakly bound, or even unbound orbits, and over many such encounters the process carves out a low-density core. Each interaction removes energy and angular momentum from the pair and transfers it to the stars, causing the pair to shrink and the stellar density near the center to drop. The mass of stars that can be ejected in this way in a single major merger is predicted to be of the same order as, or a few times larger than, the combined mass of the central pair. So observed cores in which the deficit is several times the central mass are naturally interpreted as the product of one or a small number of such major events. In NGC 5419, the large core radius, the shallow inner slope, and the substantial light and mass deficits all point to an inner structure that has been strongly modified by this type of process. The shape of the inner brightness profile carry additional information. Just outside the break radius, the decline in surface brightness with radius is still similar to that of the outer main body, but as one moves inward, the profile flattens progressively until near the center it becomes nearly constant over a finite region. This plateau, though still bright, is much less sharply peaked than the cusps seen in lower mass elliptical galaxies or in bulges without depleted cores. The transition between the outer steep region and the inner flat zone is smooth rather than abrupt, indicating that the redistribution of stars by dynamical processes has affected a substantial radial range rather than carving a hard-edged cavity. When high-resolution imaging is used to trace the profile along different directions, the core appears nearly round in projection, with only mild deviations in shape, consistent with a central region where stellar orbits have been mixed and where no strong embedded disk dominates the light. The central light profile also coexists with small-scale nuclear components, which add extra light very close to the center, but do not erase the broader deficit defined over the larger core radius. During the fitting process, these compact features can be masked or modeled separately so that the underlying core structure is still recovered, and its parameters such as break radius and inner slope are robustly estimated. The derived core radius for NGC 5449 lies at the upper end of the range observed in nearby early type galaxies, and when its value is combined with the empirical correlation between core size and central mass established for other systems, it implies a central mass of several billion solar masses in line with direct dynamical measurements. Thus, the depleted core of NGC 5419 is not only a morphological feature, but also a quantitative tracer that links the central light distribution to the mass of the central object or objects and to the history of past mergers. Within the inner kiloparsecs, the cored brightness profile therefore marks a distinct zone of the galaxy, separating the more ordinary behavior of the main stellar body from the more complex structures that appear at still smaller radii, and preserving in its shape the imprint of the processes that have reshaped the heart of this massive elliptical galaxy. In the inner regions of NGC 5419, inside the radius where the depleted stellar core has been identified, the motions of stars change in character in ways that are not immediately obvious from images alone but become clear when their velocities are mapped in detail. Every star in the galaxy follows an orbit that is determined by the combined gravitational pull of all the matter, both visible and dark, and in a massive elliptical like NGC 5419, these orbits can be grouped into broad families according to how they move around the center. Some orbits loop around a preferred axis, forming what are called tube orbits, while others wander more freely through the three-dimensional volume, filling out box-shaped regions over time. In many galaxies, the balance between these families varies with radius. In the outer body, a significant fraction of stars may be on orbits that contribute to net rotation, while closer in the mix can shift toward more symmetric motions, in which no direction is strongly preferred. To measure this balance, astronomers use integral field spectrographs that provide a spectrum at each position across the face of the galaxy. From these data, they extract maps of the line of sight velocity and of the velocity dispersion, and they also derive higher-order quantities that capture the shapes of the absorption line profiles, which carry information about how many stars move at different speeds along each line of sight. Dynamical models are then built to reproduce these maps by populating a trial gravitational potential with many orbits from the main families and adjusting their weights until the model matches both the observed light distribution and the kinematics. For NGC 54119, such orbit-based models indicate that in the central region inside the depleted core, the stellar motions become close to isotropic, meaning that the average random speed of stars is nearly the same in the radial direction along the azimuthal direction and perpendicular to the main apparent plane. In more qualitative terms, stars move with similar intensity of random motion in all directions, so that no single axis is strongly favoured. This isotropy contrasts with more anisotropic regions, where orbits may be biased toward radial paths that plunge in and out, or toward tangential paths that circle around the centre. In the inner parts of NGC 5419, the ratio between radial and tangential dispersions approaches unity, a sign that the orbital mix has been smoothed into a nearly even distribution. The velocity dispersion map in these central zones shows values that are high but relatively uniform when viewed in projection, with only gentle gradients toward the centre, and the rotation field becomes correspondingly weak, so that the dominant impression is one of random motion rather than of ordered spinning. This pattern is consistent with a central region in which many orbit families contribute, and in which box orbits and different types of tube orbits are present in comparable proportions instead of one family dominating the others. The emergence of such an isotropic centre is linked closely to the processes that formed the depleted core in the first place. When massive compact objects sink toward the centre during past mergers and form a bound pair, they interact strongly with stars whose orbits carry them close to the pair. Through repeated gravitational encounters, these stars are scattered onto new paths, often being ejected to larger radii or to high-energy orbits that carry them far from the centre. Over time, this scattering not only removes stars from the very innermost region, carving out the core, but also tends to redistribute the velocities of those that remain, erasing directional preferences and driving the velocity distribution toward isotropy. Numerical simulations that follow this process show that the central anisotropy parameter, which measures the difference between radial and tangential dispersions, is pushed towards zero in the region where the pair has been most effective at ejecting stars. Observationally, NGC 54119 fits this pattern. The inner dynamical structure inferred from orbit modelling is close to isotropic, while farther out the galaxy shows mild anisotropy, with a slight preference for radial orbits that help support its overall flattening. The inner isotropy has further implications for the stability and shape of the core. In a system where random motions are the same in all directions, small perturbations are less likely to grow into strong isometric features, and the central light distribution tends to remain smooth and nearly round in projection. This matches what is seen in high-resolution images of NGC 5419, where the core region appears as a gently flattened but otherwise regular structure, with no prominent central disk or bar to break the symmetry on these scales. The mix of orbit families that underlies this smooth appearance is complex, yet the net effect when averaged over many stars is a central zone that behaves almost like a pressure-supported fluid with no strong preferred direction for the stellar motions. At the same time, the presence of a very massive central concentration of mass ensures that orbits deep in the potential well are tightly bound and that their characteristic speeds are high. Stars near the center move swiftly in all directions, but because their motions are well mixed, the projected kinematic maps show a broad, nearly symmetric dispersion peak rather than sharp gradients in rotation. In practice, the inference of isotropy is not exact, because the observations probe only the component of motion along the line of sight, and because different combinations of orbits can within limits reproduce similar projected maps. Nevertheless, within the uncertainties, the best-fitting models consistently favor a central region in which the anisotropy is small, reinforcing the picture of a dynamically well-mixed core. In summary, the inner regions of NGC 5419 within the depleted core form an almost isotropic dynamical environment in which stars are supported against gravity by random motions that have similar strength in all directions and are arranged in a rich combination of orbit families. This nearly isotropic center marks a transition between the more anisotropic outer body, where orbital structures still retain clearer memory of past accretion along preferred directions, and the more tightly bound innermost zones of the galaxy, where stars orbit deep within the central potential well. Deeper within the inner region of NGC 5419, on scales of only a few thousands of light years, the stellar kinematics reveal a further layer of structure that is not obvious from the smooth appearance of the light alone. When astronomers construct two-dimensional maps of the line-of-sight velocities and velocity dispersions across the central parts of the galaxy using integral field spectroscopy, they find that the innermost zone behaves differently from the surrounding main body. In the previous consideration of the depleted core, the focus rests on the way the surface brightness profile becomes shallower toward the center. Here, the attention shifts to how the stars move, and to the discovery that the central region forms a kinematically distinct core. A kinematically distinct core is a central component whose mean rotation pattern differs from that of the galaxy outside it, either in amplitude in orientation, or even in the sense of rotation, so that the inner part appears to twist or decouple from the outer body when the velocity field is viewed in projection. In NGC 5419, maps of the stellar velocities show that beyond a certain radius within the inner few kiloparsecs, the net rotation follows one direction around the center. But inside that radius, the sense of rotation reverses, producing what is called a rotation flip. On one side of the galaxy, stars in the outer body move on average slightly away along the line of sight, while those on the opposite side move slightly toward indicating a gentle large-scale spin. In the kinematically distinct core, the pattern is inverted so that the inner region rotates in the opposite direction to the outer one. This contrast is subtle in amplitude because NGC 5419 remains a slow rotator overall, with random motions much stronger than ordered ones, yet it is clearly measurable when the velocity maps are examined in detail. The velocity dispersion map, which shows the spread of stellar speeds along the line of sight, remains high across both regions, so that the central area is still dominated by random motions. The distinction between core and outer body lies mainly in the sign and orientation of the small net rotation. To describe this structure quantitatively, astronomers fit simple models to the observed velocity field, decomposing it into components that describe rotation around different axes. The result for NGC 5419 is that the inner few kiloparsecs contain a distinct rotating component whose angular momentum vector is misaligned with, and in fact roughly opposite to that of the outer galaxy. The spatial extent of this kinematically distinct core is comparable to the radius over which the depleted stellar core in the brightness profile is defined, so that the same physical region of the galaxy is marked by both a flattening of the light profile and a change in the pattern of stellar rotation. In projection on the sky, the zero velocity line, which marks where the mean line of sight velocity crosses from positive to negative values, twists as it approaches the center, reflecting the transition between the rotation of the outer body and that of the inner core. This kind of central kinematic decoupling is seen in a subset of early-type galaxies and is often associated with a complex formation history involving mergers and accretion along different directions. Numerical simulations of galaxy assembly in dense environments show that when two galaxies merge with a misalignment between their spin axes and orbital angular momentum, the remnant can develop an inner component that retains the rotation pattern of one progenitor, while the outer parts carry the imprint of the other or of the orbital motion. In some cases, gas that sinks to the center during the interaction can form a rotating disk or subcomponent whose angular momentum differs from that of the main stellar body. Over time, dynamical processes can thicken such a structure and mix it with pre-existing stars, producing a kinematically distinct core that is not sharply separated in density from its surroundings but remains recognizable in velocity space. In the case of NGC 5419, the presence of a rotation flip within the depleted core suggests that its inner region has experienced at least one significant event during which material with a different angular momentum orientation was brought to the center. The isotropic velocity dispersion described earlier indicates that random motions are strong and nearly equal in all directions, yet this does not erase the small but coherent net rotation. Instead, the kinematically distinct core emerges as a subtle pattern superimposed on a strongly pressure-supported background. The combination of high dispersion and weak reversed rotation means that stars in the inner region follow orbits that, when averaged, carry a small amount of angular momentum opposite to that of the stars farther out, while still sampling a wide range of directions in three-dimensional space. From a structural point of view, the kinematically distinct core does not stand out as a separate brightness peak or as an obvious morphological substructure. High-resolution images of NGC 5419 show that the inner isophotes remain smooth and only gently flattened, with no sharply defined central disk or bar on the scales corresponding to the kinematic decoupling. The core is therefore a dynamical feature rather than a strong photometric one, and its identification relies on careful spectroscopic mapping rather than on direct inspection of images. The coexistence of a depleted stellar core in the light profile and a kinematically distinct core in the velocity field reinforces the idea that the inner region of NGC 5419 has been shaped by interactions that both removed stars from the very center and introduced material with a different angular momentum orientation. Simulations of massive galaxy mergers that include central compact objects and realistic orbital configurations reproduce similar combinations of features, large central light deficits carved out by scattering of stars off hard, central pairs and inner components that rotate in a different sense from the outer body as a result of the complex superposition of progenitor spins. In such models, the detailed properties of the kinematically distinct core, such as its size, rotation amplitude, and degree of misalignment, depend on the mass ratio of the merging galaxies, the geometry of their encounter, and the amount of gas involved, while the presence of a depleted stellar core depends primarily on the action of the central compact objects on the surrounding stars. Observationally, NGC 5419 fits naturally into the class of massive early-type galaxies, with large cores and central kinematic decoupling, and in this galaxy the kinematically distinct core forms a dynamically special inner layer embedded inside the broader main body and overlapping the depleted central zone in which the structural and dynamical signatures of past interactions are most clearly preserved. Within the depleted central core of NGC 54119 at radii of only a few hundreds of light-years from the centre, the smooth plateau of starlight that appears in lower-resolution data resolves into a more intricate structure when examined with high-quality imaging. Instead of a single peak at the very centre, high-resolution observations reveal that the brightest part of the galaxy is split into two closely spaced concentrations of light, forming what is described as a double nucleus. In images that reach the necessary angular resolution, the innermost isophotes are no longer perfectly concentric around a single central point. Rather, they show a slight elongation and a subtle saddle between two maxima, each of which is clearly extended and stellar in nature, not a single unresolved star or background object. One of these peaks lies close to the geometric centre defined by the larger scale isophotes of the galaxy, while the other is offset by a small projected distance of order, a few tens of parsecs, which corresponds to only a few hundreds of light-years at the distance of NGC 5419. The two peaks are embedded within the broader core so that the local surface brightness remains high across the entire region, but their presence breaks the simple symmetry that would characterize a single centrally peaked nucleus. To characterize this double structure, astronomers examine images taken in several bands from visible to near-infrared light and convolve model light distributions with the point spread function of the telescope to test whether the observed split could be an artifact of the imaging system. These tests show that the double peak persists after careful correction for instrumental effects, and that it appears in multiple filters, indicating that it is a genuine feature of the galaxy rather than a chance superposition of foreground stars or background galaxies along the line of sight. The colours of the two nuclei are similar to each other and resemble those of the surrounding inner core, suggesting that both are dominated by old stars, with little contribution from very young blue populations. If there are any colour differences, they are modest, perhaps reflecting slight variations in stellar metallicity or in the mix of evolved stars, but not a dramatic contrast such as would be produced by a compact recently formed star cluster embedded next to an older central component. The light profiles measured through each nucleus show that both concentrations are extended over scales of several tens of parsecs rather than being point-like, and that their surface brightness declines smoothly outwards until it merges with the plateau of the depleted core. In projection, the line connecting the two peaks is approximately aligned with one of the principal axes of the central isophotes, so that the double structure introduces a mild elongation of the innermost contours without strongly distorting the broader shape of the core. Between the two nuclei, the surface brightness dips only slightly, forming a shallow valley that emphasizes the separation but does not reach anything approaching a true gap or void. The entire region remains one of intense stellar density and high luminosity. Because the double nucleus sits inside a core whose brightness profile is already flattened relative to the outer galaxy, the additional structure appears as a superposed refinement rather than as a complete reorganization of the central light. On slightly larger scales, where the core blends into the main body, the effect of the double nucleus on the overall surface brightness profile is minor, and standard fitting procedures can still recover the global core parameters by averaging over azimuth and by modelling the faint deviations. Closer in, however, the two peaks dominate the appearance of the central arc seconds, and any attempt to trace the exact centre of the galaxy must account for their existence. Astrometric measurements that compare the positions of the two nuclei across different bands and with respect to the outer isophotes indicate that neither peak lies exactly at the photometric centre defined by the galaxy at larger radii. Rather, the true center of mass is expected to lie somewhere between them along the line that joins the peaks. This configuration is consistent with the situation in which two compact stellar concentrations orbit within the common gravitational potential of the inner galaxy, although the actual motions cannot be directly resolved because the timescales involved are long and the spatial displacements are minute on human timescales. The existence of a double nucleus also has implications for the interpretation of spectroscopic data taken with relatively large apertures centered on the galaxy. A spectrum that integrates over both peaks and the region between them will contain contributions from stars with slightly different line-of-sight velocities and dispersions, and the combined signal must be modeled carefully to avoid misinterpreting the central kinematics. In practice, integral field spectroscopy resolves the inner region into many spatial elements, and the presence of two brightness maxima is taken into account when constructing dynamical models that aim to reproduce the observed velocity and dispersion fields. Within the broader context of galaxy structure, double nuclei of this kind are known in a handful of galaxies and are often associated with complex central dynamics and with the presence of multiple compact concentrations that have not yet fully merged. In NGC 5419, the double nucleus coexists with the depleted stellar core and the kinematically distinct inner region already described, forming a layered central structure in which the light distribution, the rotation pattern, and the orbital mix all change on scales of only a few hundreds to a few thousands of light years. The double nucleus itself represents the most immediately visible manifestation of this complexity in direct images, a pair of closely spaced stellar condensations that sit at the heart of the galaxy's core and define on the smallest resolve scales the structure of its central light. Around the double nucleus of SGC 5419, on scales of only a few hundreds of light years, the inner core resolves into a very dense nuclear region where stars, gas, and a compact central power source all share the same deep gravitational well. In lower resolution views, this area appears as a smooth, bright plateau at the center of the depleted core, but high-quality imaging and spectroscopy show that this plateau is built from an exceptionally crowded nuclear star field wrapped around the two light peaks, together with a very compact source of non-stellar emission at the photometric center. This stellar background in this region is continuous with the depleted core described earlier yet. The local surface brightness rises still further toward the two nuclei so that the immediate surroundings of the pair form the brightest part of the galaxy. Individual stars cannot be resolved at the distance of NGC 5419. Instead, their combined light produces a grainy but essentially smooth glow, whose color is very similar to that of the surrounding core, indicating that the nuclear star field is made mainly of old stars with only modest variations in chemical composition from place to place. Any color differences between the two peaks and the surrounding plateau are small, and can be explained by subtle changes in the mix of evolved stars or by the presence of a faint extra source of non-stellar light at the exact center, rather than by a young starburst or a strongly distinct stellar population. At the geometric center defined by the larger scale isophotes, high-resolution images reveal a point-like source that remains unresolved even with fine angular resolution. Its spectrum in the central spatial element shows an extra continuum component and weak emission features that do not match the signature of an ordinary star cluster, but instead resemble those of a compact active nucleus. An active galactic nucleus is a small region at the core of a galaxy where gas falling toward a very massive central object releases energy and radiation, and sometimes in jets. In NGC 5419, the nuclear source is faint compared with the stellar background, so it is classed as a low luminosity active nucleus rather than a powerful quasar. Its presence contributes only a small fraction of the total light in the innermost tens of parsecs, but provides clear evidence that some gas is still being accreted in the very centre, and that the central gravitational potential is deep enough to draw material inward from the surrounding core. Slightly offset from this point source lies the second nucleus, an extended stellar concentration whose peak is displaced by roughly a few dozens of parsecs in projection, corresponding to a separation of order a few hundreds of light-years between the two brightness maxima. This secondary nucleus has no strong non-stellar point source at its centre in the observed bands. Its light profile looks more like that of a compact nuclear star cluster or a dense remnant of a former galaxy core extended over several tens of parsecs and smoothly merging into the ambient nuclear star field. The line joining the two nuclei aligns approximately with one of the principal axes of the central isophotes, so that together they introduce a mild elongation of the innermost contours without breaking the overall symmetry of the depleted core. Between them, the surface brightness dips only slightly, forming a shallow saddle rather than a dark gap, and the underlying stellar density remains extremely high across the entire region. Spectroscopic observations that resolve the inner core into many spatial elements show that the random motions of stars around the double nucleus are particularly strong. Outside the nuclear region, within the depleted core, but away from the two peaks, the stellar velocity dispersion already has a large value reflecting the deep central potential. As one moves inward toward the line connecting the nuclei, the dispersion rises further, reaching a broad maximum in the area where the two light concentrations overlap along the line of sight. This pattern indicates that stars in the immediate surroundings of the nuclei move on very tightly bound orbits, with speeds of several hundreds of kilometers per second, and that the gravitational field in this region is steeper than in the rest of the core. The map of velocity dispersion thus shows a central ridge or peak, associated with the double nucleus superimposed on the high, but more uniform dispersion of the depleted core as a whole. At the same time, the average line of sight velocity across the nuclear region follows the reversed rotation pattern of the kinematically distinct core, but the net rotational speeds remain small compared with the random ones, so the nuclear star field is still dominated by pressure support rather than by a rapidly spinning disk. Gas in the central few hundreds of light-years is scarce but not entirely absent. Emission lines detected in nuclear spectra point to a small amount of ionized gas close to the photometric center most likely associated with the low luminosity active nucleus. This gas does not form bright extended structures like those seen in some more strongly active galaxies. Instead, it appears as a compact nuclear component whose luminosity is low compared with the stellar continuum. There is little evidence for massive reservoirs of cold gas, or for vigorous recent star formation in the immediate neighbourhood of the nuclei. The nuclear region, therefore, seems to be in a state where a tenuous supply of gas, perhaps drawn from the hot atmosphere or from slowly cooling material in the inner core, is sufficient to maintain a faint active nucleus, but not to build a large young central disk or to trigger a strong starburst. On somewhat larger scales, beyond the inner few tens of parsecs, but still within the depleted core, the interstellar medium is dominated by very low-density hot gas that blends into the broader intragroup and intracluster medium described earlier, and any dust present is confined to small low-contrast features that do not strongly affect the appearance of the double nucleus. In radio and high-energy observations, NGC 5419 shows evidence for past or present nuclear activity at a low level consistent with the presence of a compact active source at the center, but on the spatial scales considered here, The most prominent features remain the two stellar nuclei and the surrounding high-dispersion star field. Taken together, these observations build a picture in which the immediate environment of the double nucleus is a very dense old stellar system with extremely high random velocities threaded by a small amount of ionized gas and centered on a faint but real active nucleus. The central point source at the photocenter, the offset extended secondary nucleus, and the steep local enhancement in velocity dispersion all coexist within the same few hundreds of light-years, defining a nuclear environment that is more complex than a single smooth star cluster, yet still embedded in the broader depleted core of the galaxy. Within this environment, any star gas cloud or compact object moves under the influence of a gravitational field that is stronger and more sharply peaked than in any other part of NGC 5419, and the layered structure of light and motion in the nuclear region sets the immediate stage for the still smaller scales on which the central massive concentration or concentrations reside. At the very heart of NGC 5419 inside the region, where the double nucleus and the steep rise in stellar velocity dispersion mark the deepest part of the gravitational well, lies a central concentration of mass, so compact and so dense that it cannot be made of stars or gas alone. Astronomers interpret this central mass as a pair of supermassive black holes, a binary system in which two extremely massive dark objects orbit around their common center of gravity. A black hole of this kind is a region of space-time where the gravitational field is so strong that nothing, not even light, can escape once it passes a certain boundary called the event horizon. Because black holes themselves do not emit light, their presence in a galaxy like NGC 5419 is inferred indirectly from the way their gravity affects the motions of nearby stars and gas, and from the faint radiation produced when gas falls toward them and is heated. In the case of NGC 5419, the existence of a very massive central concentration and of a likely binary is revealed by the combination of several observed features in the inner core: the large depleted stellar core, the almost isotropic distribution of stellar orbits in the center, the kinematically distinct central region, with its rotation flip and the double nucleus, with a separation of only a few tens of parsecs, corresponding to only a few hundreds of light-years. Together, these structural and dynamical signatures point to a scenario in which two supermassive black holes brought together by past mergers of massive galaxies now inhabit the central region and have not yet fully merged into a single object. To quantify the mass of this central concentration, astronomers build dynamical models that attempt to reproduce in detail both the observed light distribution and the maps of stellar velocities and velocity dispersions across the galaxy. These models begin with a gravitational potential that includes contributions from the star's the dark matter halo and a central compact mass that represents the combined effect of the black hole or black holes. Within this potential, many possible stellar orbits are calculated sampling the main families of box orbits and tube orbits that can exist in such a triaxial system. The models then assign weights to these orbits so that their superposition matches the observed surface brightness and the line-of-sight velocity distributions at all measured positions. By varying the amount of central mass and the shape and scale of the dark matter halo, and by comparing the resulting kinematic predictions with the data, the models identify the combination of parameters that best fits the observations. In earlier work focused on the inner core of NGC 5419 orbit-based models, applied to high-resolution stellar kinematics outside the immediate region of the double nucleus, yielded a central mass of several billions of times the mass of the Sun, specifically of the order of 7 billion solar masses, with uncertainties of a few billions of solar masses in either direction. This value already placed the central black hole among the more massive ones known in nearby galaxies, and was consistent with empirical relations between black hole mass and properties of the host galaxy, such as the stellar velocity dispersion and the size of the depleted core. More recent dynamical studies have extended this approach using higher quality integral field spectroscopic data that cover the central region in greater detail and that allow for more flexible traxial models of the galaxy's potential. These improved models take into account the nearly isotropic orbital distribution in the inner core, the presence of the kinematically distinct central region, and the complex shape of the light profile, and they explore a wider range of possible combinations of stellar mass dark matter and central compact mass. When these more advanced models are fitted to the data for NGC 5419, they indicate that the total mass of the central compact component or components is about 10 billion times the mass of the Sun, with an uncertainty that is small compared with the value itself. Because the spatial resolution of the data does not allow the individual event horizons of the two black holes to be resolved, the dynamical models measure only the combined gravitational effect of the pair, not the masses of the individual objects separately. Nevertheless, the total mass inferred from the stellar motions matches well the expectations based on the size and depth of the depleted core, and on the empirical correlations between core properties and black hole mass derived from samples of other galaxies. This agreement supports the interpretation that the double nucleus indeed marks the locations of two supermassive black holes, whose combined mass is around 10 billion solar masses. The fact that different modeling approaches using different data sets and assumptions converge on a similar mass scale increases confidence in the result even though systematic uncertainties remain. For example, the exact shape of the dark matter halo, the ratio between stellar mass and light, and the three-dimensional orbital distribution all affect the detailed mapping between the observed stellar kinematics and the inferred central mass. Within the range of plausible choices for these ingredients, however, the models consistently require a very massive central compact component to reproduce the high velocity dispersion and the subtle patterns in the velocity maps. If the total mass of the binary is close to 10 billion times the mass of the Sun, then each individual black hole likely carries a mass of several billions of solar masses, although the exact division between them is not yet constrained by observations. The separation between the two nuclei in projection of order, a few tens of parsecs, implies that the black holes are relatively close in terms of the gravitational scales defined by their total mass, and that they reside deep within the same central potential well. At such separations, dynamical friction from the surrounding stars has already brought the black holes together from much larger distances, and the pair is expected to be gravitationally bound, orbiting around their common center of mass, even if the details of that orbit cannot be resolved in current data. The strong rise in velocity dispersion observed in the region of the double nucleus and the almost isotropic central orbital structure both follow naturally from the presence of such a massive central pair, which accelerates nearby stars to high speeds and scatters them in many directions. In this way, the dynamical models, the photometric structure of the core, and the detailed kinematics of the nuclear region all come together to indicate that at the center of NGC 5419 there is a binary of supermassive black holes whose combined mass is about 10 billion times the mass of the Sun, providing the dominant contribution to the gravitational potential on the smallest scales resolved in the galaxy and shaping the motions of stars in its immediate vicinity. In the immediate surroundings of the central binary in NGC 5419, gravity is dominated almost entirely by the combined mass of the two supermassive black holes, and the influence of the surrounding stars and dark matter becomes a secondary contribution. Astronomers describe the region where the central mass outweighs the enclosed stellar mass as the sphere of influence, a roughly spherical zone within which the gravitational field is set primarily by the black holes rather than by the stars. For a total mass of about 10 billion times the mass of the Sun, this sphere of influence in NGC 5419 extends over distances of the order of a few tens to perhaps a few hundreds of light years, comparable to or somewhat larger than the projected separation between the two nuclei. Inside this region, the orbital speeds required to remain bound become very high, and stars on low-energy orbits move with velocities of many hundreds of kilometers per second, along tightly curved paths around the shared center of mass of the binary. Each individual black hole has its own event horizon, a boundary at a small radius, where the escape speed reaches the speed of light, but on the scales resolved in NGC 5419, these horizons are far too small to be seen directly. Instead, what can be traced is the combined effect of the binary on the orbits of nearby stars. Stars that pass close to the pair experience strong gravitational deflections. Some are scattered onto more tightly bound orbits. Others are flung outward to larger radii, and a small fraction can be accelerated to speeds high enough to escape from the galaxy entirely. The region of phase space occupied by orbits that bring stars close to the binary is sometimes called the loss cone, because stars that enter it can be lost from the central region through ejection or through capture by one of the black holes. In NGC 5419, the large, depleted stellar core already indicates that many stars have been removed from the innermost zone over long timescales by such interactions, and the present-day nuclear star field represents those that remain on orbits that either avoid the most dangerous passages or have not yet been scattered. Within the sphere of influence, the gravitational potential is steep, and the orbital periods of stars become short compared with those at larger radii. A star whose orbit carries it to within a few light years of the binary can complete a circuit around the center in a time measured in only a few 100,000 years, which is brief on galactic timescales, and the cumulative effect of many orbits and many encounters gradually reshapes the distribution of velocities into the nearly isotropic pattern inferred from the kinematic models. Very close to each black hole within a region called the tidal radius, the differential pull of gravity between the near and far sides of a star can exceed the star's own self-gravity, leading to tidal disruption. In such an event, the star is torn apart, and part of its gas can be captured into a temporary accretion flow that produces a luminous flare before the material is either swallowed or expelled. While no such flare is currently identified in NGC 5419, theoretical studies of galaxies with similar central masses show that these rare events contribute to the long-term evolution of the population of stars on low angular momentum orbits near the binary. On larger but still nuclear scales, gas clouds that drift into the sphere of influence feel the same strong focusing by gravity. If cold gas is present, it can lose angular momentum through collisions and interactions, spiraling inward until it forms an accretion flow around one or both black holes. As gas falls deeper into the potential well, gravitational energy is converted into heat and radiation, giving rise to the phenomenon known as an active galactic nucleus. In NGC 5419, the active nucleus is faint compared with those of classical quasars. The central compact source detected at the photocenter emits only modest amounts of radiation, relative to the Eddington limit, the theoretical rate at which radiation pressure would balance gravity for the given mass, implying that the current accretion rate is very low compared with the maximum possible. The nuclear environment therefore appears to be in a quiet state, where the supply of gas reaching the immediate vicinity of the binary is limited, and any outflows or jets driven by accretion are weak. Radio observations and high-energy data indicate only a low level of nuclear activity, consistent with the scenario in which the black holes accrete slowly from the hot low-density gas of the inner core rather than from a large reservoir of cold, dense material. This quiet state has important consequences for the appearance of the central region. In galaxies with vigorously accreting black holes, bright accretion disks and powerful jets can dominate the central luminosity and strongly disturb the surrounding gas and stars. In NGC 5419, by contrast, the luminosity of the nuclear source is small compared with the stellar background, and the morphology of the central star field remains smooth and only gently modified by any feedback from the active nucleus. The primary imprint of the binary on its environment is dynamical rather than radiative. It reshapes stellar orbits, carves out the depleted core, raises the central velocity dispersion, and defines the steepest part of the gravitational potential, but it does so in a way that leaves the nuclear region photometrically dominated by old stars rather than by non-stellar light. General relativity predicts that a binary of supermassive black holes also emits gravitational waves, ripples in spacetime that carry away energy and angular momentum from the orbit. For a pair with a combined mass of about 10 billion solar masses and a separation of tens of light years, the orbital period is very long, and the corresponding gravitational waves have extremely low frequencies of the order of billionths of a hertz. At such large separations, the rate of energy lost to gravitational radiation is slow, and other processes such as interactions with stars and gas play a more important role in shrinking the orbit. The binary in NGC 5419 therefore resides in a regime where it perturbs its stellar environment strongly, yet evolves only gradually under the influence of gravitational waves, contributing in principle to a very low-frequency background, but doing so in a way that is not individually measurable with current techniques. On the scale of the sphere of influence, the presence of the binary also defines a natural boundary between different regimes of stellar dynamics. Outside this zone, stars respond mainly to the combined gravity of the galaxy's stars and dark matter halo, and their motions can be described in terms of the global potential of the elliptical galaxy. Inside it, trajectories are more strongly curved around the central mass, and small changes in initial conditions can lead to large differences in orbits over time, a behavior that increases the efficiency with which stars are scattered into or out of the loss cone. Numerical models of stellar motion in such potentials show that the region around a massive binary is often characterized by a complex mixture of regular and chaotic orbits, with some stars trapped in resonant configurations, and others wandering through large volumes of phase space before being either ejected or captured. In NGC 5419, the nearly isotropic velocity distribution inferred in the inner core suggests that many of these complex processes have been at work long enough to erase directional preferences in the population that remains bound. In summary, the immediate surroundings of the central binary in NGC 5419 form a compact, dynamically intense environment in which the gravity of two supermassive black holes, together about 10 billion times as massive as the Sun, dominates the motion of stars and gas over distances of tens to hundreds of light years. Within this sphere of influence, stars move on high-speed orbits shaped by the steep central potential. Some are scattered outward or inward. Through close encounters with the binary, and a faint trickle of gas maintains a low luminosity active nucleus at the photocenter, all while the bulk of the nuclear light continues to come from an old dense stellar population. The binary itself remains electromagnetically quiet by the standards of luminous quasars, yet it sets the dynamical conditions in the very center of the galaxy and provides the final inner layer of the nested structures that define the core of NGC 5419.